there could be maybe different ways of doing this, but one example of doing this is to find the decision boundary. Okay. But then now, so basically we have reduced the problem of classifying new data to a problem of finding a decision boundary, right? So now then, how do we find this decision boundary? There is also many different ways of doing this, but one way of doing this is via what's called support vector machine. Okay, so I'm not going to all the great details about support vector machines, but for now you can take it as one way of finding this decision boundary. Okay. Then because now we know this decision boundary, if this data was on the left-hand side of the boundary, then it should be labeled as orange. But if the data is on the right-hand side of the decision boundary, then it's labeled as blue. So labeling becomes really easy once you know the decision boundary. Okay, and also what you might have noticed that when we define this decision boundary, not all data has been used. So you see that only these two and these three. Only there are 3 data points have been used to find these decision boundaries. Okay, so when we say support vectors, these are the data points or data vectors that are used to define this decision boundary. Okay, and we can also express this prediction function or classification function in this form. So basically, so here now, these are some weights that goes with the training data. So this is non-zero. So this will be 0 if the data that we use for finding the decision boundary is not support vector. So if it's not used for finding, so for like these 2 data and this data, if they're not used for finding decision boundary, so they will be 0 in this equation. And this function called K is a kernel function, and it basically measures how the similarity, like it quantifies the similarity between the data that's given, like the training data, and the new data that we try to classify. So basically, like this equation, you can see this is really the weighted sum of the similarity function. Okay. Okay, so maybe we can continue. Okay, so the previous example is quite straightforward, but now what if our raw data is given in this form, such that we cannot, it's not immediately apparent how to draw a linear decision boundary. Then we apply what's called feature map. So we basically map our raw data into high dimensional feature space in which we can find the hyperplane that separates this data. Okay. So in this new space, the kernel function, which tells us the similarity between training data and test data, can be given as an inner product in this space. Okay. Sorry. So what kernel theory tells us is that if this kernel function satisfies a certain property, then there must exist a high-dimensional feature space in which the kernel is an inner product. So, intuitively, this means that if this kernel function satisfies a certain condition, then there must exist a map, like a feature map, such that we can find a linear decision boundary or hyperplane in the new feature space. Okay, so if I use the example of classifying an image of an animal, you can intuitively think of it as as a raw data, you're only given the color of the animal. So, and of course, if you just try to classify whether a given image is a dog or a cat by only looking at its color, it's difficult. But you can add more feature to the data by adding like the shape of the ear or shape of the tail and so on. You add more feature to the data, and it becomes easier and easier to classify. Okay. And and so now people thought, okay, maybe we can use quantum computing because we know quantum Hilbert space is large; it grows exponentially with respect to the number of qubits. So can we exploit the large Hilbert space of quantum state for doing this? Like, can we use Hilbert space as a feature space? Okay, so our work was actually to realize a simple kernel-based binary classifier, but it's not really the same as support vector machine because we did not it's what we did was still non-parametric, so we did not optimize the weights for finding support that's non-zero only for support vectors. So basically, it's more like KNN type. So basically, we used all the data that's available, but it's a distance-based binary classification. Okay, so now, like, of course, an important question is how do we represent a given classical data as a quantum state? And one way of doing this is called amplitude encoding, and the idea is to basically use the probability amplitudes of qubits, basically. So here, like for example, we're given n-dimensional data, and these elements in this n-dimensional vector will be, of course, it has to be normalized, but basically it's directly encoded as a probability amplitude of log n qubits. Okay, and now let's say we have more than one vector. So let's say we have m vectors, and each vector is n-dimensional vector. Then now we can use log n times m qubits and just write this this number as a probability amplitude of log n times m qubits. Okay, so this is one way of representing classical data as a quantum state, and there is also what's called quantum feature mapping. So here we define we can define a unitary transformation. We can parameterize a unitary transformation using classical data that we like to encode into a quantum state. So for example, we're given like one-dimensional data, and we want to encode it into qubit. We define some unitary transformation, and then if we kind of think about it visually, then basically this one-dimensional data has been mapped onto a block sphere, such that it becomes much easier to find linear, like much easier to draw a hyperplane that separates this data. Okay, but here what's important is that this unitary transformation has to be hard to simulate classically. Otherwise, you can use classical computer to do the same task. And also here, the number of qubits scale linearly with the dimension of the data. Okay, so these are two different. There are more ways of doing representing classical data to quantum state, but these are two like popular examples. Okay. So now, how do we realize the classifier? So so the classification is actually quite simple as long as we are given a special state. So for now, we're gonna forget about all the details of how to really like realize the state preparation step on a quantum circuit. But let's say this is like a black box. We're given a state that encodes classical data here. So this could be amplitude encoding, or it could be the quantum feature map. It doesn't really matter. But this is a representation of classical data as a quantum state, and it's entangled with label qubits. So this should be either 0 or 1. So if it's 0, it's like a class -1. If it's 1, then it's class +1. And it also has like an index qubit to index, which data it is. Okay. Then now we're given a test data and an ancilla qubit, and we basically perform a simple swap test. And after swap test, we look at the 2-qubit observable. Okay. And what's interesting here is that if we just follow a simple circuit followed by a 2-qubit measurement, the outcome of this 2-qubit measurement, so we're measuring like the expectation value, right? This looks a lot like the prediction function that we saw before. Okay, so this again becomes a weighted sum of the kernel function, where the kernel function is given as a state overlap between training data and test data. And we can raise this power by using many copies of this test data and training data, basically. So we have some control over this. And we can also control this parameter by changing this parameter here when we do the state preparation. Okay. Then once we have this, we do simple post-processing to decide the label of this new test data. Okay. So I'm kind of running out of time, so I'll try to go a bit fast. So first interesting remark is that, if we really look into the details of this formulation, it looks a lot similar to quantum state discrimination. It's not exactly a quantum state discrimination because we're still measuring an expectation value, but it seems like it's there is some connection between quantum state discrimination and quantum classification. And also, second remark is that this scheme provides some sort of robustness to Pauli errors. So it's kind of easy to see that because we are only measuring 2-qubit observable, as long as the errors that effectively appear as Pauli error at the end of the circuit, which commutes with sigma z, of course, that does not do any harm to our measurement, right? So it's automatically robust to such errors. However, now if an error that effectively appears as a Pauli error at the end of the circuit, which does not commute with sigma z, then what happens to our outcome is that it only scales linearly with the error rate. Okay, but however, you have to remember that in the end, we're only concerned about the sign of the measurement because we only want to classify whether this is like +1 or -1, right? So now we don't really care about the magnitude of this value, but only the sign of this value. We can basically repeat this measurement many times, such that we are more confident about the sign of the value, right? And then the number of repetition is only polynomial, quadratic with respect to the error rate. Okay. So like just to kind of summarize, the advantage of this scheme is that, first of all, as long as we can realize this state preparation, then it automatically gives us exponential data compression. And when you also, secondly, if you look at this classification step, the number of gates that we need to use in this classification scales linearly with the number of qubits, meaning that it scales logarithmically with respect to the data size. And we always do 2-qubit measurement regardless of the data size, so it could be nice. And also, finally, by the nature of this problem, we only need to know the sign of the outcome. So when we try to implement this on a quantum computer, it could provide some robustness to the coherence. Okay, so we designed a simple toy problem and implemented on a real quantum computer. So basically, we used we used cloud access to IBM Quantum Experience. But when we were doing this experiment, we had an access to only 5-qubit device. So we had to find a problem that fits with the 5-qubit device. So we had to come up with very simple, some artificial data set that's just good enough for proof of principle. So this is really like a proof of principle that was designed to be executed on a 5-qubit device on IBM Quantum Experience. Okay. And the summary is that when we did the experiment, it worked quite well. So if you look at this figure, if you look at this plot, so x-axis parameterizes the test data. So basically, and the y-axis basically tells us the sign of this classification. So if it's plus, then it should have been classified as +1. If it's minus, it should be classified as -1. And then we have different classes for different test data given on the x-axis. Okay, so this solid line is theory, and this red triangle is what we get from the experiment. And there is some deviation, of course, in the magnitude. However, remember, we only care about the sign of this by the nature of the problem. So you can see that actually the classification is done almost 100% correctly. Like there's only one data that was not classified correctly. Just to briefly tell you this slide. So basically, this classification, it consists of some gates, but some gates followed by 2-qubit measurement. But this could really be mapped. This could also just be as this whole classification step could just be thought of as measuring a specific observable on the test data, training data, and the label qubit. Okay, so we can really simplify this scheme further if we are given an oracle that generates this data set. Okay, so now we can also think about single-shot classification, because we can describe the entire classification step as measuring a certain observable, right? Because we define the observable, we can define a projective measurement, so we can now think about single-shot classification. Okay, and what's interesting is that if we look at the single-shot behavior, then we can do the classification by seeing whether the measured eigenvalue is +1 or -1, right? And there is also associated error to this measurement. And when you look at the error in this scheme, then the Hellstrom operator, which is used for quantum state discrimination, appears again. So, I mean, we didn't really look into this deeply, but there seems to be, so the message that I'm trying to convey here is that there seems to be some deep connection between quantum classification and quantum state discrimination. By using a different, slightly different form of initial state, we can also do ensemble learning. We can do like a linear, we can do a convex sum over many different learning models. Just it naturally comes from the linearity of quantum mechanics. So it's quite straightforward to design an ensemble learning based on our scheme. And finally, if we have a different type, if we have slightly more complicated state preparation in this black box, then we can actually also recover a quantum support vector machine. Okay, so let me summarize. So basically, we've designed a distance-based binary classifier with the quantum state overlap as a kernel function. Okay, so this could provide exponential compression of data and also exponentially less number of gates with respect to the dimension and size of the data. So this circuit is relatively simple, and it only requires 2-qubit measurement, which could be 2-qubit measurement regardless of the dimension of the data and the number of data, which could be useful if we really want to implement it on the real hardware. Okay, and we expect that this could be useful for machine learning in a high-dimensional feature space. Okay, so I'm a little bit over time, but I will end here and I'll take questions if there are any.
Okay, is there any question? You can speak on the...
So are there any questions?
Yeah, you can speak on the audio, or you can type in the chatting board, please.
Maybe because we are 5 minutes behind, maybe I should just stop now. And if you have questions, you feel free to leave your questions on the chatting board, and I'll try to answer them.
That'd be great. Okay, well, thank you very much, Dr. Daniel Park, for the nice presentation. And so the question can be raised in the chatting board, and he will be responding to it. And we want to move to the next presentation.